Chris is, if I were to talk a bit about Chris's CV, there would be no time left for the presentation. Chris has been in the field for over 20 years, started at the Air Force Research Laboratory and is currently at the University of Dayton. Chris is by far an acknowledged subject matter and international expert in thin films. Chris has 4 patents. He's published over 80 peer-reviewed articles and served as the guest editor for surface coatings technology and thin solid films. So without any further ado, let me please introduce you to my friend and our good fortune to have Chris Muratore. Thank you. Chris, go at it.
Well, thanks, Frank. I don't know if I've ever had anyone introduce me as their friend before. That was the nicest title or honor that anyone's ever mentioned before giving a talk or a seminar like this one. So thank you. I'm very happy to be here and happy to talk about a topic that I think about a lot, is flexible electronics. So let me see. There's 2 very different areas that I'm interested in. One is high-powered flexible electronics, and we'll see why that's seemingly kind of a paradox based on fundamentals of material science and physics. Getting materials that are capable of carrying high currents and performing well under high power circumstances, integrating those into a flexible platform is not straightforward. And also there's a lot of highly functional materials that are very thin, a few molecules thick, that we can integrate into flexible electronics, and they're intrinsically flexible even though they're semiconducting materials. So those are 2 areas of interest to me. First, let me just tell you a little bit about where I am. I'm sorry that we can't all be together, but at least I can bring a little bit of where I am to you. So here is Dayton, Ohio. It's in the southwest corner of Ohio. And here's so Dayton, Ohio is a famous place in some ways, at least to some people, because this is where the Wright brothers lived, who are considered the inventors of aviation. And this is the campus at the University of Dayton. We're a Catholic institution. This is what it looks like right now. It's very green. There's lots of trees around here. This is the building that I'm in, and I'm actually in the diametrically opposed corner. I'm in this corner of the building up on the top floor. And so I get to look at this beautiful view, and my house is actually right around here somewhere, buried in these trees. So I don't know if you can see this picture. This is a picture taken from the roof of our building in the opposite direction, and the campus is lovely at nighttime. One of the nice things about the University of Dayton is that we're close to the Air Force Research Laboratory. It's about 10 miles away. And so we do a lot of work with the Air Force and collaborate often. We have their people come to the university and vice versa, our people work there. So I mentioned these 2 different applications for flexible electronics, and both of them are related to this concept of ambient computing. That is, having devices do things without us telling them to do them. And there's a lot of applications for sensors in this respect. So this is a tooth-mounted sensor that's designed to interact with particular types of bacteria. So you could imagine an interface between a sensor like this and your toothbrush, right? And there's a red light that blinks on your toothbrush until you've got a sufficiently low concentration of these bacteria in your mouth. And then maybe you get a green light and you know you're done brushing your teeth. Maybe you can say the ABCs or do something and it will give you a similar result, but this is nice. And there's actually some really important implications of dental hygiene. So in 2019, there's a link. Every single Alzheimer's patient has a bacteria in their brain that does not belong there, and it comes from your mouth. And so for decades, scientists realized there was this correlation. It was kind of a loose correlation between older folks having dental surgery and the onset of Alzheimer's disease. And it turns out that you would have this kind of interaction of the bacteria with the blood. It would be transported to the brain and induce Alzheimer's. So that is something singing the ABCs while you brush your teeth will not give you, right? It's kind of specificity in terms of these particular bacteria that can lead to serious health issues. There's other applications for flexible electronics. So it's important to be flexible here because you want it to fit onto your tooth, and everyone's tooth is different. You don't want to custom fabricate a device for everybody's tooth. You want to have one that's going to fit on anybody's tooth. So by introducing this aspect of flexibility, it's conformal electronics, you can make a one-size-fits-all device for lots of different people or lots of different devices, lots of different entities that you may want to attach a sensor to. Making flexible electronics inexpensively is important if you want to integrate them into food packaging, right? So lots of food is wasted in our country, at least. I've read, higher than 30% of the food that's produced and ready to eat is wasted because it spoils. Having a digital system or a system that you could integrate into a network to help keep track of the freshness of food would eliminate a lot of that waste. I work with the Air Force a lot, and sensors that you can wear are really important to them. You have pilots that operate on both sides of the spectrum, right? You have pilots that are flying these $100+ million machines with all kinds of sophisticated functionality. It's pretty thrilling to fly one of those. It can be a little bit taxing to be engaged in a thrilling event for a long time. So monitoring fatigue and stress levels in pilots is important for reducing mistakes and injuries as well. And you have drone pilots who spend a lot of time doing not much of anything, and maybe helping them to know when they need a break by monitoring the concentration of different kinds of biomolecules in their sweat or in their saliva can help modulate their performance and optimize their ability to do their job. So these are materials, I would say, with high functionality. You can do a lot to the surfaces of these materials to make them do specifically what you want, to look for a particular bacteria or a particular biomolecule and give you an answer. So we also talked about high power flexible electronics. And I think one of the coolest applications for this, that's a major component for ambient computing, is a hardwareless interface, right? So maybe you see like a cool science fiction movie where people just move their fingers in the air and something happens, right? So in this case, a person's making the ubiquitous sign for expand, expand the view on my touchscreen device. And that's exactly what's going to happen to this map as they rub their fingers together. They can zoom in or zoom out. And to have that kind of spatial resolution, it takes radar. So you can't really just use like a camera to watch somebody's finger motion and have that sensitive response that's needed for interfacing with an electronic device. You really need to use radar, and radar takes high power. You've got to send out a pretty powerful beam, and that explains why this watch. So if you want to learn more about these hardwareless interfaces, you could look up Google Soli, S-O-L-I. They have a couple of patents right now and are developing this technology. I think they're kind of at the forefront of it. But this takes high power, and high power is not really compatible with flexible electronics for some reasons that we'll expand on as we talk today. So this is a slide that I'm going to show twice. These are the summary and conclusions as well as the outline and introduction. So you can pay attention if there's something here that you're really interested in. You could be watching for our discussion of that. If nothing here is interesting to you, maybe it's a beautiful day here, maybe enjoying the outdoors would be a better thing to do than being here. But these are the things that we're going to talk about. So we're going to talk about a couple of different ways that you can attain flexible electronic devices. One is to just use materials that are flexible anyway, like polymers, right? So we can make devices out of polymers. And that's probably the most advanced and most well-developed, that's the most well-developed aspect of what we'll talk about today is polymer-based electronics have been around for a long time. So we won't talk too much about that, but there's some things we can learn about using polymers to integrate flexible electronic devices. The other thing you can do is you can use materials that are useful for their electronic properties in the device application, and they're not flexible because they're just not. If you make those materials thin, then you can use them for flexible applications. One of the things we can do is we can make an electronic device which oftentimes requires some serious structural demands, like we'll use principles of like epitaxy, where the layers that you're growing to make your device emulate the structure of the substrate. And, you know, if you want to put these on a polymer or glass or some kind of thin glass, some kind of flexible substrate, you're not going to have that kind of advantage. Maybe you require very high processing temperatures. Again, not really compatible with polymer. And so what we can do is use the right substrate to make our materials and then tear the material off of that substrate and put it on a new substrate. So we'll talk about how to do that. One way to get to device fabrication for flexible applications is by printing materials. So we can take small particles, spray them onto a surface, allow them to coalesce, and then use their functionality once it's an intact material. So we'll talk about some of the fundamental principles of transfer. We're going to talk about materials that, again, are usually rigid, but when you make them thin, sometimes we'll refer to these as two-dimensional materials. These are materials that are generally 5 molecular layers thick or thinner than that. These materials are a way to get to flexible devices as well. If we're talking about using polymer substrates, which are useful, right? They're intrinsically flexible, low cost, easy to synthesize. Typically, the thermal conductivity of polymers is poor, and so that can be a challenge, especially if you're talking about using high-powered devices, right, where there's lots of heat to be dissipated. Where does it go? Silicon has a very high thermal conductivity. It's very easy to manage heat. You can attach it to a heat sink, and the heat disappears. When we have polymers, it's not so easy. You have to do something. And then maybe we can talk again about how some of these electronic devices, how some of these flexible electronics ideas can really change our life. So if you think about what makes a material flexible, you think about like a put it together yourself bookshelf, right? So if you don't put it together correctly, it's going to wobble. It's going to be really easy to shear one shelf over the other. There's no directionality in terms of the way that it's connected, and the connections are all pretty loose. And so when you think about ductile materials, I think about metals, right? Metals, the atoms just kind of slide over each other because the electrons are just communally shared between all the nuclei of the metals. No electron belongs to any particular nuclei, so everything is just kind of flowing along pretty easily. When you think about materials that are effective semiconductors, that's not what they're like at all. There's typically possession of these electrons and some directionality in the bonding. I think of directionality and bonding like adding some brackets to the corners of this bookcase so that it's not so easy to shear. And in fact, I looked for this plot on Google and couldn't find it, so I made it myself. And I was surprised that no one had made it before. But if you consider the mechanical properties, so elastic modulus is just the stiffness of a material, versus the band gap. A band gap is kind of this fundamental semiconducting property of materials. There's a pretty good correlation. The bigger the band gap, which in a way kind of indicates how useful the semiconducting material is in an application like a transistor where it's a switch, right? Where you want to be able to turn it on and off. You want to sometimes, especially for some of the sensor applications we're talking about, some other applications, you want to have a substantial band gap. And so you've got to have stiff material if you want to have a decent band gap. And so these elastic moduli are much, much, much higher, you know, an order of magnitude or two higher than lots of polymers. And so it seems like it might be a little bit of a puzzle to integrate these materials into flexible applications. So I mentioned before, one way to get to bulk materials that are useful for devices like semiconducting materials is to make them super thin. And you can see how the thickness correlates to the amount of strain that you can put into a material. Right? When you think about what makes a material flexible, well, you can put a lot of strain into it and it doesn't get ruined. It doesn't become permanently deformed or permanently decomposed. So when I think about putting a material on a flexible substrate, I can think about it like this. So these are the atoms of the material. And I bend it and I get some strain between those atoms. Now, this is a one atom thick situation. If I do the same thing and I can bend it in what I'll call tension or compression, this is just the opposite of this. If I put these balls on the inside here, I'd be in compression on this side of the substrate and I'm in a tension on top of the substrate. Well, if I add additional layers and I bend this, and in this case, let's say I'm bending it in compression, you can see that as the thickness increases, the distance between the atoms also increases. So my strain increases with thickness. So if I want to maximize the amount of strain that I can put into a material, if I want to make a material flexible, I want to make it thin, because that's a way to minimize the distance between the atoms as it gets bent or stretched or whatever. So thin materials are a nice way to do it. Let's show a demonstration of that. So I have this rock. Oh, I'm sorry. So I have this rock. This is a mineral called muscovite, or it's also known as mica. And you can see it's not transparent. Like, I cannot see, you can't see my face through it, and I can't see the screen. But if I tear a sheet of it off, so I'm going to tear, I don't know if you can see this. It looks like I just took some packing tape off of it. But this is a layer of this muscovite, and you can see from this schematic of its molecular structure, I have these covalently bound layers that are separated by these layers with only a few bonds. That's where I just broke this thing, at some one of these junctions between these covalently bound layers and another one of those layers. I have this kind of weak layer, and I just separated this from this. And this thin layer, look, you can see me through it, and I can bend it. Like, I can make it be super flexible. So this is just a demonstration of how you can make materials thin and totally change their properties. I cannot bend this bulk rock, and I can easily bend this sheet, this little fragment of the rock. So that's just a way to show what happens when you make these materials thin. This is not one atom thick, by the way, as my schematic in the past suggested. It's probably more like 80 microns thick. So that's about the limit. I can make silicon less than 100 microns thick, and it becomes fairly flexible. I can make it way thinner than that, and it becomes really, really flexible. And you can see here, so on this graph, I've got, let's just say this is the elastic modulus. This is the stiffness of the material, how resistant it is to deformation, and this is how thick it is on the x-axis. Well, I can set up a relationship where I have the thickness where the material demonstrates bulk properties. I plug in the bulk elastic modulus, which is something that's pretty easy to find on Google or to measure it yourself. And this is how much strain that I can put into the material in the plane of the material. And this is Poisson's ratio. Poisson's ratio is just a constant. It's around 0.25 for just about any material. So I can take this elastic modulus for bulk silicon and plug it in, and I can see what the thickness is below which I start to deviate from the bulk elastic modulus. And so it's about 80 nanometers, right? So around here, I start to deviate substantially from the elastic modulus. So I can make a calculation that helps me to know what kind of thickness range do I need before this material really changes its properties and starts to become a lot more flexible. So if making materials thinner is a way to get to flex, then how can we do it? There's a few ways. One common way is to just grind the material away. And so there's all kinds of commercial equipment you can buy to make silicon wafers be thinner, or any kind of wafer be thinner, and just build a device upon it. And that's kind of nice. If you get the thickness right, you can still use the structural aspects of silicon to deposit materials and grow your devices straight onto the substrate. You would have to do some grinding before you wanted to do etching, because etching's not quite as fast as grinding. But if you want to have a very precise thickness, or if you want to maybe reduce the amount of damage that's done on the surface, because this is going to introduce all kinds of dislocations if you do a grinding process, make your wafer thinner, etching can be a more gentle way to reduce the thickness of the material. One way that we'll focus on a lot today is layer transfer. So you just find a way to tear the material off of a surface. Maybe you grow the material on a surface with some kind of sacrificial layer underneath, or you sacrifice a substrate. You choose a substrate that's easy to cleave, and you tear the material off and make it thin that way. So we'll talk about in more detail about how to get to some of these. I did want to show you these super thin silicon wafers. So I think this is 18 inches. I have maybe like a 10-inch wafer that is like this in my lab. And this is just, you bend it like a sheet of paper. I mean, it really is flexible. And it started off as a rigid bulk piece of silicon. It can be a little bit hard to handle these, wafers that are of uniform thinness so that they're flexible. There are some processes that grind the material preferentially, leaving a ring on the outside, and that gives you a rigid framework. This is like carrying a canvas, like a painting, and this is like having a framed painting here. It's maybe a little easier to manage without introducing damage. So once you make that silicon thin, you need to do stuff to it, right? You've got to add the other components of the device that are going to make it do something interesting. And so one of the ways to do that is through transfer processes. And so there are different ways to do it. It's a lot like an old-fashioned stamp, right? So you could buy a stamp with your signature on it or a date on it or with some pattern on it that is going to be useful for your device. And you ink the stamp. Now, it's probably not going to be the same as the ink that you use at the post office to put the postmark on your postage stamp or something like that. Maybe it has more functionality, but it's the same principle. You put that ink all over the surface. There's parts of the surface that are raised, and then you apply the stamp to the surface to transfer the material that's on your stamp to that surface, right? So that's a fairly familiar process if you've been to the library, maybe 5 years ago or later, earlier than that rather, then you've seen people use a stamp where they would stamp the due date into your book. There's other things you can do. You could take the stamp and peel it, apply it to a surface and peel it, and then you have that ink stuck to your stamp. There's some other things you can do that are a little more sophisticated. So I have an array of ink here on the surface. I can apply the stamp to that ink, and I can only select some of these features onto my stamp. And then I can take that stamp and put these features somewhere else. The way to do that is by controlling the strain rate of the stamp. So for any of these transfer processes, if you've ever used an old-fashioned stamp, you've got to press it into the ink and press it onto the surface pretty hard. And the magnitude of the stress that you apply and the rate at which you apply that stress have a lot to do with the performance of this transfer process. So the idea of a transfer process is very valuable because what it allows us to do is kind of decouple the process kinetics of making the device from the limitations of the substrate. So if I want to take a GaN device, GaN is a process, is a super high temperature. It requires all kinds of constraints on what substrate you use and its structure, right? You have to use a particular structure, oftentimes sapphire, and you have to put a epitaxial layer that's a good buffer between the GaN and the substrate. And then you have to grow the GaN to be pretty thick so that it becomes dislocation free and it has the electronic properties that you want. You could never grow GaN directly onto a polymer substrate or most flexible substrates. But what you can do is grow it on a perfect substrate, do everything you need to make great GaN, and then just tear it off of that surface and stick it to a polymer substrate. And we'll show you some results of what happens when you do that. But this idea of decoupling the kinetics of synthesis and fabrication from the substrate is a valuable one, and transfer is kind of necessary to do that. So here's some nice images of a stamp that's being applied to, let's say, some ink. Let's say we want to pick this green thing up with our stamp. And so I can change the rate at which I strain the stamp. This stamp has these pyramids at the corners. You can see them here, right? So this is what it looks like initially. When I squish the stamp down, this is what it looks like. And I can control the rate at which I push that stamp down, and it's going to change the response of these features on the surface. So polymers, I don't know, I think of polymers and they're always kind of bendy, right? But it depends on the rate at which you apply the strain. If you apply the strain rate at a high enough rate, you can totally change the mechanical properties of the polymer, and that's shown here. So this is a stress strain curve. We talked about elastic modulus before as the stiffness of the material. The elastic modulus is simply the slope of these lines of this stress strain curve. And these lines correspond to stress applied to the same material at different rates. And the rates are listed here. So you can see that this strain rate 1 is higher than the rest. It's like a factor of 20 higher than the last one. And you can see what happens to the stiffness of the material. It gets less and less stiff as that rate gets smaller and smaller. And so I'm a chewing gum addict right now. And if we were in a classroom, I'm chewing some gum right now. I could take it out of my mouth and stretch it. It's kind of gross, but I could stretch it out at a slow rate. But if I throw it against the wall, it's just going to bounce off, like I threw a rock at the wall. So this idea of controlling the response of the polymer material by controlling the strain rate is useful, because I can strain it quickly in some places and not have transfer because the material is not as compliant, and I can strain it slowly in other places and end up picking up the material off of the surface. So by controlling the strain rate, I control the stamping ability or the pickup ability of these polymer materials. Why is that? It's just a fundamental property of polymers. If you think about how an amorphous polymer is constructed, you've got these polymer chains. They're super strong along their own axis. They're covalently bound carbon, but the interactions between these chains is really weak. And so when I apply a stress to these polymer chains, I can align them. I'm going to make them slide over each other when they undergo this alignment process. The rate at which I do that is going to dictate the response of the material. So if I do it slowly, those chains have lots of time to slide over each other and to deconvolute themselves into a line structure like the one that's shown here. When I apply the stress quickly, there's no time for these things to detangle from each other. And so the response is a lot different. The material seems a lot more rigid. So the way that these polymers behave on a molecular scale dictates their response kind of on the macro scale that we can see and feel and use to transfer these materials. And so what I want to do is when I want to pick up the material, right, I want it to stick to the surface. And so I can control this velocity at which I deform the stamp. And when I want to detach the thing I picked up and put it on the substrate, then I want to operate at a different deformation velocity, right? So I can do this simple energy balance depending on what I want to do. If I want to if I want to deposit the ink onto the receiver or the substrate, then I need to make sure that that I've got the right kind of adhesive energy from the ink that I want to print. So again, by changing the rate of deformation of these stamps, I can control whether I'm picking up or dropping off material from the surface of that stamp. So that's one way to do it. I mentioned a little earlier that another way to do it is to introduce a sacrificial layer between the substrate and the material that's going to be a part of your device. And we talked about GaN in particular. GaN is a moderately high band gap material. It's useful for high power electronics. And to grow it, usually grow it on a sapphire substrate, you put an aluminum nitride layer between the sapphire and the GaN. And this does some things. It kind of matches. It's a good buffer between the lattice parameter of the GaN and the sapphire, and you can accommodate some stress in this layer. And what we've done here is introduced boron nitride between this stack that's for the GaN and the substrate. And boron nitride has a super low shear strength. It's very easy to tear it apart, just like it has a structure that's a lot like this mica. It's really easy for me to tear a sheet off of the mica, and it's really easy to break this hexagonal boron nitride layer, which is like 3 or 4 or 5 layers. It's easy to split it in two. And so you can grow this GaN device and then tear the material off and attach it to another substrate. This happens to be a pretty remarkable process. The mobility, right, which is an important parameter in a high power transistor device. The mobility stays really high even after transfer and strain. And so the way to do that is you use a stamp, you pick it up, but now we're controlling the dynamics of how it detaches from the substrate, less from our interface with the stamp and more from the mechanical properties of this interface, this kind of sacrificial interface layer. There's other ways to do this. You can use layers that absorb lasers to be the sacrificial layer, and we'll talk about that. So that's kind of in this graphic. If we were going to spend more time together today, we would probably talk in some detail about all of these laser-based processes for flexible electronics. There's a lot of advantages to using lasers when you want to make flexible devices because it's a way to introduce heat locally rather than globally. You don't have to stick the whole sample into an oven and heat it up. You can just heat where you want using the laser. So an example is like if you have these, 2 nanowires that are not making a good connection with each other because there's a bunch of junk on the surface, well, you could anneal them and have them make great contact. But maybe they're on a polymer and the annealing temperature is going to exceed the decomposition temperature of the polymer. So if you use a laser where these materials absorb the laser preferentially over the surrounding polymer substrate, you're going to have heating where you want it at the interface and not in the polymer. Maybe the laser passes right through the polymer and doesn't heat it up at all. Now, on the contrary, what we're going to do here is we used a low shear layer, that boron nitride layer, to detach the GaN device from the substrate in the previous example. What we're going to do here, you're going to use a laser, and we're going to have a sacrificial layer between our device and the substrate. That sacrificial layer is going to be a great absorber of the wavelength of laser that we're using, so that it basically ablates. As we pass the laser over the surface, through the underside of this device, right? The device is up here, here's the substrate, and here's the sacrificial layer that I'm annihilating with the laser because it absorbs the laser energy preferentially. This substrate allows the laser to pass through, and I'm ablating this sacrificial layer, enabling transfer of the device here. Another thing you can do with a laser is lots of times you want to have transparency in an electronic device. But if you need to have an electrical contact, most conductive materials, they're not transparent. This is kind of something that we just have to live with. It's dictated by the laws of physics, right? If it's conductive, then it's not going to be transparent. But what you can do is you can maintain a continuous network of a metal, which again is going to be opaque, but you could punch a bunch of holes in it with a laser, even on a polymer surface, and then it becomes transparent and conductive. So there's lots of tools that lasers enable that are useful for flexible electronic materials. We talked about two approaches for making flexible electronics. One is making materials thin, and we showed some ways to do that. We'll talk about some more ways. The other is to just use materials that are intrinsically flexible, and polymers are fitting into that category, right? We talked about the flexibility of polymers, and we have a lot of control over just how flexible they are, how stiff they are. So this is kind of resembling, this is a little schematic that's like this amorphous polymer I talked about before. You have these polymer chains, they're covalently bound, carbons all in a line, and they interact weakly between each other. So they're very strong along a chain, very weak between chains. There's things I could do to strengthen the interactions between chains. I could add these branches, and they interfere with each other as I try and deform this material. Remember what we talked about when we talked about stretching the polymer out. These chains are all tangled up, and they have to untwist from each other. Well, if I make it hard to untwist them from each other, I'm going to make the polymer more stiff. Again, also chemically bond them together. So this is like cross-link. This is what is the difference between an eraser and a hockey puck is cross-linking, right? An eraser is super soft because it's more like this. A hockey puck is super hard because it's been vulcanized. There's elements you can add to the polymer like sulfur, and you can induce these strong bonds between the chains. And a network polymer is basically just a highly cross-linked polymer, maybe a slightly different details in the chemistry. But you get the idea. If I link these chains together strongly, covalently, then I'm going to have a much stiffer polymer material. So I can control the properties of these polymers, not just their mechanical properties, but also their electronic properties. And the way I'm going to control their electronic properties is by selecting polymer monomers that have the structure and properties that I'm looking for. So when I think of polymers, I think all polymers are dielectric, and that's not really true. There's some special semiconducting and conductive polymers. Most polymers are pretty good dielectrics. Their dielectric strength depends on how easy it is to induce polarization. And so if you can separate the charge in the actual molecules that make up the polymer, then it's going to be a better dielectric, because that's what a dielectric does, right? It separates charge. So you can look at the monomer and see some characteristics that will induce higher polarization. That'll be a stronger dielectric. So it's also possible to make polymer chains that are semiconducting. And when we talk about semiconductors, we talk about p-dope semiconductors or p-type semiconductors and n-type. P-type, they are a little shy on electrons, right? So conduction occurs through holes, which a hole is just like an absence of an electron, which an absence of an electron would carry a positive charge, which is what the P stands for. And so it doesn't matter what kind of carrier you've got. If you have a charge carrier, you're going to have a conductor or a semiconductor. The difference between a conductor and a semiconductor is with a semiconductor, you can control the conductivity, right? So
Dr. Muratore, excuse me for interrupting, but we
Yeah.
appear to have lost your audio. Can you check your audio settings, please?
Oh, that's very strange. Hey, Frank, is that any better? Can you hear me now?
Chris, I think we can, some of us can hear it.
Perhaps I've lost your audio. Scott, can you indicate whether or not you can hear Chris, please?
Hey, yeah, I'm talking now.
I can hear Chris. Can you hear me?
I can hear you, Scott.
Okay,
I
I can hear
Frank
you.
can. So, Frank, it looks like it's...
Chris, apologies, but it looks like Mary Ellen and Scott can hear you, so please continue. Apologies for the interruption.
Yeah. No, I'm glad, because I didn't change anything, so I'm really glad I didn't lose my audio. I was nervous there for a second. So we can see some characteristics of p-type semiconductors. Typically, you'll see these fused rings, like rings that are adjacent to each other. And this will give us the, I actually changed some of my audio settings here in an attempt to allow Frank to hear me. Let me readjust those. There we go. So when you see these rings that are fused together, these are generally going to be p-type semiconducting polymers. There we go. N-type semiconducting polymers, they will have slightly different structures. I think that there's some challenges associated with using N-type semiconducting polymers. One of them is that the ambient environment is filled with molecules that want to attach to these surfaces and will dope them. And that kind of defeats the purpose of having a semiconductor in lots of applications. You want to be in charge of whether it's conducting or not conducting by applying a gate voltage or some kind of potential. If they're automatically or inadvertently being functionalized by the ambient environment and turning conductive, that's not super useful. So there's definitely some challenges associated with using N-type semiconducting polymers. When you want to make an electronic device out of conducting polymers, and again, you can buy, I could go to Walmart and buy a device that's made out of organic polymers or organic semiconductors and polymer devices. So I'm not going to talk a ton about that here today, but one thing that is useful for in terms of polymers is you can take two different materials and put them together. You can take two different monomers, where a monomer is like one of these molecular groups that we were talking about. A polymer is simply a string of these all put together. So you can take two different monomers, make a bunch of chains of each of those monomers, and put those chains together, and then you can optimize properties. Like, say, in a display, you want it to be bright, so you want it to luminesce brightly. You want it to have a high luminescence efficiency. But you also want the charge to be, the charge carrying capability to be maximized, the charge mobility to be maximized. There's going to be two different materials that give you those two different properties. But what's nice is that you can take these two different monomers that give you this different functionality and put them together to make a single device. So that, in one aspect, is a really useful feature for polymers. Working with polymers can be a little bit of a challenge if you want to apply materials to the surface. So in general, polymers have low surface energies. And when materials have low surface energies and you want to attach something to the surface, it tends to ball up or not wet on the surface. Sometimes when you want to use polymers as a substrate or for actual material, like let's say you want to put contacts on your semiconducting polymer, you may have to change the surface properties of that polymer to get better adhesion and contact of the metal onto the surface. And there's different ways to do that. You can use acid or you can use plasma to change that surface energy to get better contact between the metals and the polymers. When you're using polymer-based substrates, there's some nice games that you can play. So when you apply a material to a polymer surface, if that polymer has a very low elastic modulus, so we're talking about silicon having an elastic modulus of 150 gigapascals. So look at this. So this is a polymer material. This is polystyrene. I'm pretty sure this is polystyrene. It's either polystyrene or PDMS, which is another kind of ubiquitous polymer material used for flexible electronics. You see the modulus is like almost a factor of 100, right? Or more than a factor of 100 lower than the elastic modulus for silicon. These are very, very flexible materials. They're not stiff at all. You can make big changes in the elastic modulus. Imagine applying a film, like let's say we put a metal, or let's say we put a silicon film on this polymer. Well, it's got a much higher elastic modulus, and so there's going to be some interfacial stress whenever you have a big elastic modulus mismatch between materials at an interface. You're going to have some stresses. And lots of times you'll see buckling of the polymer to accommodate that interfacial stress. And generally that magnitude of that stress increases with the thickness of the film. And so you can see changes in the deformation of the polymer depending on the thickness of the material that you've added to it. You can also adjust the modulus of these polymers themselves. So we use PDMS a lot. And this is a very common surface characteristic of PDMS is when you put a film on top of it, actually even when you put it in vacuum, if you attach it to a substrate and put it in vacuum, the top expands and you have some changes in the morphology, and then you deposit material on it and you take it out of vacuum and it contracts and you have these buckles. These buckles can actually be really useful because they act, if I want to stretch this material out, before I really start deforming the material that I've put on the surface, I'm extending this buckled region, right? I'm going to flatten the material out, and I haven't even really applied any strain to the material I've deposited on top. So that's one really useful aspect of using these polymers, is that you can introduce this buckling, and that gives you a little bit of like free pre-strain. You can stretch this thing out before you start to really apply some stress onto the film. We'll look at some examples of materials that have been pre-stressed and what happens when you stretch them out in terms of their electronic properties. I'm going to skip that one. So using polymers, materials that are intrinsically flexible in their bulk form, is one way to achieve these flexible electronics, but another way is to use materials that, again, in bulk form, they are stiff, but when you make them very thin, they become flexible. And not only do these materials become flexible, lots of times they have some really interesting functionality added to them when they're thin. Their performance is a lot different than you'd expect. So we can talk about 3 different types of very thin materials. So graphene was kind of the first, right? And we won't spend too much time talking about graphene. It's got kind of limited capacity, but we learned a lot from graphene, and it opened the doors for materials with lots of different electronic properties and enhanced functionality. One example that is commonly used and really interesting, in part because some of these transition metal dichalcogenides are very naturally abundant. If we're going to use flexible electronics for ambient computing applications, there's going to be devices everywhere, and they can't cost very much to produce. And in lots of cases, you want them to be disposable. And so using materials that are naturally abundant can be really helpful just for reducing costs. These MXenes, these are materials that are electrically conductive. You know, there's useful applications for flexible batteries. And in MXenes, I'm not going to talk about them today just because our time's a little bit limited, but for all this discussion, if we're going to have flexible devices, then we probably, in most cases, need flexible power supplies as well. And MXenes are one way to get to these flexible power supplies. So graphene is, in a sense, not something new, right? So I guess 2004 is where we say the first paper on graphene was. Back in 1947, people were talking about single layer graphite, which is exactly what the definition of graphene is in theory. It turns out to be a super interesting material in theory, but it took a really long time to get here, right? So this is kind of the paper that is that marks the birth of graphene from 2004. And you wonder, why did it take so long to get there? Well, it's not easy to isolate the graphene. We'll talk about how Novoselev and Geim did it. We'll also talk a little bit about why it's so interesting. So, I mean, you can joke and say, hey, if you used a pencil, then you've made graphene, because you've taken a big chunk of graphite and rubbed it on a surface and transferred it, and some of what you've written will be as thin as a single layer of carbon. But it's really hard to find it, and it took some things lining up to be able to find it. One of them was visualization through a technique other than transmission electron microscopy, because it would take more than a lifetime. If you wrote a page with a pencil, it would probably take a lifetime to analyze that page, looking for a single layer of graphite using a transmission electron microscope. So the ability to see the thickness of graphene from optical contrast on a silicon oxide wafer was something that people hadn't thought of before, and turned out to be pretty useful. Atomic force microscopy is a pretty definitive technique to measure the thickness and prove that you've really got a single layer, show how many layers you've got. And that's, you know, a relatively new technique, and it's not super fast. Again, it would take a long time to analyze an entire sheet of paper written on with a pencil to look for that graphene with an atomic force microscope or an AFM. And so, you know, all these things, these materials are so thin, it's hard to see. Sometimes they'll joke, it's like the emperor's new material, right? If you're smart enough, you can see it. If you're not, you can't. And no one wants to admit that they can't see it, because we all want to be smart. So Geim and Novoselev, they use this very simple Scotch tape method, kind of like this muscovite or mica that I showed you before. It's super easy to peel apart a layer. You know, I couldn't do that with a chunk of steel, right? I couldn't just peel. I'd like to think that I'm in good shape, but I could not just peel an atomic layer of steel off of a bulk piece. But with graphite, there's a similar situation, right? You've got these covalently bound sheets. They're very strong, and they're separated by these van der Waals gaps that makes their bonding out of plane very weak. And so it's very easy to tear apart a single crystal of graphite. And if you're very lucky, you'll have some fraction of the material that you've torn apart be only a single layer. And so there's this is the way that it was done, and this is a great way to make very small volumes of material for laboratory characterization. If you want to make larger samples and you want to use them for an application, a common way to make graphene is through chemical vapor deposition. And here's a bunch of different recipes for making graphene using chemical vapor deposition. This is just where you pass gaseous precursors over substrates that are heated, and through thermal decomposition of the gaseous precursors, you form a film on the surface. There's kind of a couple of ways that you can use CVD to make graphene in large quantities or in large areas. Most of the time, people use copper, and copper it has very limited solubility of carbon. And so you get a carbon film forming on the surface. So you can see nucleation at these grain boundaries, right? So you have preferential starting of these crystals at the grain boundaries of the copper substrate. You can control the grain structure of that copper substrate to change the nucleation density and therefore the grain size of the graphene that's forming on the surface. You know, another way that people have made graphene is with nickel. So nickel has a higher solubility for carbon, and the carbon diffuses into the nickel. You cool it down, and the graphene precipitates out of the nickel as it becomes less soluble with temperature. So here are the phase diagrams for nickel and carbon and for copper and carbon. And the scale is way different, right? You're looking at this and saying, hey, the solubility of carbon and copper is much greater, but no, look, this is 0.005 weight percent, whereas this is like more like 5 weight percent. So we've got a huge difference, like a factor of 1,000 difference in the solubility of carbon in these two different metals, hence the different growth mechanisms for graphene. So, all right, it's great to grow it on a metal, but you can't really do any characterization of this material on a metal, especially because graphene is pretty conductive. In fact, it can be one of the most electrically conductive materials that we know of. So if you want to do some characterization, you got to take it off of that copper and put it onto something that's insulating. And so another transfer method is to apply a polymer to the surface, like all over the surface. So PMMA is this polymer that's just spin coated on the surface, and then digest the metal on the backside. And now you've got graphene attached to the polymer. Then you could just throw the polymer in some acetone. Well, actually, I guess you want to you take this polymer and graphene, stick it on your substrate, and then throw it in some acetone. The polymer dissolves, and now you've got graphene adhered to your substrate. When you do this process, it's not without consequence. Lots of times you'll end up with some features in the graphene that compromise its amazing properties, right? So graphene is super strong and super thermally and electrically conductive and all these things, but once we start to mess with the structure and introduce these defects, we start to lose some of that capacity. And not only that, it's not easy to maintain the thickness of something that's one atomic layer thick over a huge area. And so you can see in this micrograph, you know, this is big, it's 10 microns, but you can see there's lots of differences in thickness. This is like an AFM trace on the surface that's showing you the thickness, and you can see it's not uniform over a line drawn across that surface. So graphene is exciting and awesome. It's a little bit hard to implement realistically, but there's been a lot of progress. People have worked really hard on this because it has so much promise. And so in this paper, you can see transfer over a 30-inch span here, right? So this is huge. This is like, I don't know, like a square meter of material almost. And there's graphene or something like graphene transferred over a lot of the surface to make a massive flexible display. So thermal tape is another tool that's used for transfer. It's sticky at one temperature and not sticky at a different temperature. So you can go either way. You can make it sticky when it's hot or not sticky when it's hot. And being able to turn off and on its ability to stick, it's a variation of what we talked about with the strain rate of those polymer stamps. So you can take the tape, stick it onto the surface, get transfer from the one surface and apply it to another by turning off the stickiness of the tape. So graphene, again, in theory, it's fantastic. It's got all these incredible attributes that are listed here, right? It's transparent. It's a transparent conductor, which is something that we talked about before. It's like something that we haven't really been able to realize before, and compromises the performance of lots of systems, especially like solar panels. But it's a little hard to realize all these features on a large scale. You know, another, graphene is just part of the picture too, right? If we want to make a flexible device, we need more than just a conductor. We need semiconductors and insulators, right? Those are the three: conductors, semiconductors, and insulators are the three components we need to make a real device. And so we need something that has the flexibility of graphene, but some of the other properties that it doesn't. And so graphene came around in 2004. In 2010, an analog to graphene that is a great semiconducting material with a band gap of 1.8 eV was brought forth. And now we can really start to do something with these 2D materials. So there's different ways to make them. I'll show you some alternative ways, and then we'll talk about some more mainstream ways. One alternative is to apply an amorphous MOS2 material on a polymer at room temperature and then use a laser to crystallize that material to give it its semiconducting properties. And that's pretty useful. You can do some patterning and you can see what happens. Again, lasers are this kind of heavy artillery for flexible electronics, because in this case, the semiconducting material, the MOS2, absorbs the visible laser. It's like a 532 nanometer laser, and the polymer doesn't. So this material gets heated to temperatures in excess of 500 degrees, but the thermal conductivity or the thermal interface conductance between the material and the polymer is very poor. And so this material gets hot, the polymer doesn't absorb the laser and doesn't have a lot of heat conductance or thermal transmission from this polymer to the semiconducting material. And so you end up achieving high temperatures for annealing without decomposing the polymer. And a laser is useful because you can write features in the surface and induce crystallinity of these materials. But the problem with a laser is that the beam width is narrow, right? So these are like 5 micron diameter patterns. These are the crystalline lines in this amorphous material. This is on PDMS. You can see some of those ripples that we talked about before on the surface of this image. You don't have to use a laser. You can use a broadband, like a xenon lamp, as an optical source. And you can expose the amorphous material to energy in the form of this light and crystallize it over a much larger scale simultaneously, right? So you can do this over a square meter. You could buy a commercial photonic curing system that will anneal a square meter at a time, and you can convert these materials from amorphous to crystalline to give you properties such as, you know, light detection, right? So we've turned it into a semiconducting material, so we introduce some energy and we can induce a current to promote motion of electrons and use this as a photoconductor. We can use all the same techniques that we talked about for graphene too, right? You could do a mechanical exfoliation process where you take some tape and separate the material until it's the thickness that you want. That's a pretty low throughput process. It's hard to make a lot of material in a day using that technique. Another exfoliation technique that's analogous but gives you a much higher yield is chemical exfoliation, which is usually done in the liquid phase. And so you take a bulk crystal, so this could be powder or it could be, you know, a naturally occurring crystal. You immerse it in some solvent and you introduce some energy. Typically sonication is the form of energy. And through cavitation and other processes, maybe some chemistry with the solvent, depending on what you're using, you can break this crystal apart. So you can introduce the energy as an alternative to the mechanical energy for cleaving this crystal. This sonication energy can break the material apart. If you want this suspension to be stable, right, if you don't want these particles to segregate out because of density differences, transition metal dicalcitonizers are usually made of pretty heavy elements, then you want to pick a solvent that has around the same surface tension as the surface energy of the material that you're exfoliating. This is out of place, so we'll skip it. once you have a solution of these particles, you can do all kinds of things with them, right? You could take a drop and put it on a surface and you'll have a small volume of this exfoliated material left behind as the solvent evaporates. But if you want to do something in a more controlled way, you could take this suspension of particles and print it onto a surface. And there's lots of different ways to print particles on the surfaces. All of them have a lot of challenges, right? Because over time, you preferentially lose the solvent, so your concentration of the particles increases with time. You will inevitably, as the solvent evaporates, you'll change the viscosity of the solution, and you'll inevitably clog the printing head. There's a lot of challenges associated with printing, but it's still a pretty attractive technique because you can put this array of particles on the surface in the pattern that you want at room temperature. Use a laser to make them coalesce, where you have preferential heating of the particles, not the substrate, and form this continuous network of particles with the properties that you want. So we're taking these tools that we talked about, using a few of them at a time to make these electronic devices. You know, I apologize. I just looked at the clock and it's a little bit late. I hope that it's not too much. I'm glad Frank gave me the provision to last until 90 minutes. So this is just an array of different solvents with graphene suspensions over time, right? So this is the freshly made material, and you can see just about all of them look black because the graphene is homogeneously suspended throughout the volume of the solvent. You can see there's some that look a little more transparent than others. So there's a lot of mismatch between the surface energy and surface energy of graphene and the surface tension of these two solvents. So you see a few of the suspensions stay stable. And this is, again, just due to this good surface energy matching. There's other ways that you can induce stability in these suspensions. And there's costs and benefits associated with this. You can attach polymers, you can functionalize the particles with polymers, and you get this kind of steric repulsion, right? So you have these kind of complicated arrays of atoms with electrostatic forces that'll interact with adjacent flakes that are functionalized this way and push them apart. And this is a way to induce stability in the suspension, which is useful for a practical application for like printing and stuff. So here's some other examples of nanoparticles that are functionalized to keep them from aggregating, right? If you have very small particles, there's a driving force for them to aggregate together. And you can inhibit that aggregation by attaching these polymers on the surface. Now the trouble is, let's think about what we want to do. We want to have a stable suspension of these particles so that we can apply them to a surface, and the process isn't going to change over time. But once they're on the surface, we want them to interact with each other. If I'm putting silver on a surface, I'm probably trying to make a wire or like some conductive network of particles. And if they're all covered with these polymers, that's really going to inhibit their ability to conduct electricity. And so I need to do something afterwards to be able to remove the stuff from the surface. And this is another place where a laser synthesis or a laser processing step is really useful. You can also just do conventional annealing, and lots of printed electronics require some kind of annealing step afterwards. Sometimes the temperatures are extreme, up to 400 degrees C. Lots of times if you're applying electrical contacts via printing onto a semiconducting surface to make some kind of device, you've got to anneal it at a pretty high temperature to make it work. Again, a laser provides an opportunity to provide that annealing without decomposition of the polymer substrate. You can print the different kinds of polymers that are directly used to make devices as well, right? We're talking about putting things on the surface of a polymer. The polymer is just a substrate here, a way to carry the interesting parts of the device. You can also print polymers that can be integrated into devices on their own without integration of any particles or any other phases besides the polymer itself. So if you want to make these polymers and want to apply them to a surface or make a stack like you might need to make a device, there's different techniques. One is vacuum thermal evaporation. And this is kind of just like any evaporation, except you're using these polymer precursors and inducing decomposition with an electron beam and getting coalescence of these decomposition products on the surface. So that's good. but it's a little hard to use on a regular basis or to use commercially because you've got these, you've got a lack of thermal conduction in the polymer precursor that you're shooting the electron beam at. It's a lot different than metal electron beam evaporation. And these kind of discontinuities in the thermal profile, you don't have heat uniformly spread throughout the volume of material, and so you end up with these pockets of material, and the deposition rate over time is usually not so uniform. You can do like an organic phase deposition, organic vapor phase deposition, where you blow the precursors into the chamber and you kind of take care of making them homogeneous before they're introduced into the system to aggregate or coalesce on the substrate. So vacuum thermal evaporation is useful for investigative studies. If you want to make large areas or make production polymers, then you probably want to use some kind of organic vapor phase technique. I'm going to skip this. I mentioned earlier that one of the big challenges with flexible electronics is thermal management. So just like the band gap varies with elastic modulus, thermal conductivity varies with elastic modulus too. For materials that aren't electrically conductive, the higher the elastic modulus, the higher the thermal conductivity. So if you're using polymers, which are super flexible with a low elastic modulus, thermal conductivity is also going to be really poor. And so what can we do to help with that? One thing we need to be careful is I love nanotechnology, but when you have things that are nano size, they tend to trap heat because the heat needs to propagate over some distance. There's a characteristic length associated with phononic heat transfer, atomic vibrations, which occur when you have a material that's not electrically conductive. This mean free path is lots of times on the order of nanometers, and so if you have very tiny features and tiny materials, you can inhibit thermal conduction through this material. But one thing you can do is just make the flexible substrate a little more thermally conductive, and it doesn't take much to make a big difference in device performance and lifetime. So here, this is these GaN devices that we talked about before. So these are high-power electronic devices with high-power densities. You're looking at this and saying, hey, 50 milliwatts is not high power. Well, it is when you normalize it over the volume of material that's integrated into this device. It's very high power density. But if you just increase the thermal conductivity of the polymer, so PDMS is a polymer, this is a polymer composite that just has some conductive additive material in it, you get a big change in the temperature at the surface of this device as a function of power, right? So we can just take a power like 20 watts and you can see, or 20 milliwatts, at 20 milliwatts I've got a temperature of like 65 or 67 degrees here and 77 degrees here. So every 10 degrees is about it's like a factor of 50% increase in lifetime for electronics, more or less. And so it doesn't take much to reduce the thermal burden on these flexible electronics. Just some considerations of thermal management from the onset is a good place to start. You can see the consequences of poor thermal management in a device. So those GaN devices were grown on a sapphire substrate. Sapphire is a very high thermal conductivity. Let's say it's 100 watts per meter Kelvin. PDMS has a very low thermal conductivity. Let's say it's 1 watt per meter Kelvin. That's a little bit generous. It's less than that. It's more like 0.2. But you have this big difference in the ability to dissipate heat from this device when it's on this flexible substrate. And I cannot pass as much current through it, right? I start to have these changes in the performance of the device when I'm passing smaller currents through it. Now, if I compare the as-grown, so this is without any kind of transfer. This is the as-grown MBE GaN on a sapphire substrate. When I transfer it to a polymer that's more thermally conductive, I can put more power through it. Not quite as much as on the as-grown device, but certainly a lot more than on just the polymer device. And I don't have these kind of strange effects that compromise the performance of the device. So what happens when you strain these electronics, when you start to bend them? It's really what we need to be able to do for these flexible electronics. We start to introduce defects in the surface that compromise the ability to conduct electricity. And so if you have a crack in the surface, and it's pretty difficult to pass electrons through that crack. And this is just showing you what happens. You know, most flexible electronics, we want to use them more than once. We probably want to use them for lots and lots of cycles. But the first cycle, you see what happens is you strain the material and then you bend it back, and then you do that 100 times, and then you see that you have this shift, right, in the resistance and the bending radius. You're getting much higher resistances at much smaller bending radii. The bending radius, kind of the smaller it is, the sharper the bend we're putting into the material. So this number gets smaller, kind of the more strain we're putting into the material. And you can see that we have this shift in performance. This is just from accumulation of these defects associated with deformation of the materials over time. Some materials, their properties, like their optical properties and their electronic properties, will change as you strain them. And it's really important to take that into account. So this is an example where the band gap in one of these 2D transition metal dichalcogenides shifts with strain. And that's kind of important if you're counting on your device to perform a certain way. You need to know that some of the intrinsic properties of that material are not so intrinsic. When you strain them, they're going to be different. So you need to be aware of how the optical properties change with strain. This is kind of more of the same, just the change in resistance as a function of strain. And it depends what kind of strain you've got. Compressive strain tends to push the atoms together, where tensile strain tends to pull them apart. And if we have a large area, like a big graphene display, we're going to have lots of defects, and a tensile stress is going to kind of pull the material apart at those defects. We did it. This is a repeat of the slide that we saw early on. We saw some things about processing flexible electronic materials and different tools that we can use. And we saw how they perform when we use them the right way, like when we strain them, and how they might degrade. So I will end at this point, and I'm happy to talk about any questions that you might have. Again, Frank, thank you for the invitation to participate, and thank you for those who came to join us today.
Chris, thank you. I don't see any questions on the Q&A. Folks, now's your time to add something to the Q&A if you'd like Chris to address anything specific. I think, Chris, you may have intimidated all of us. I know you've intimidated me with your incredible command of the subject matter. So let me thank you and thank all of our. Oh, there is something on here. Oh, we have Andrew coming in again. Let me echo. Absolutely fantastic presentation. One more time, folks. You will all be receiving Chris's direct contact information in the next few days, and we'll be posting up this presentation to our YouTube channel as soon as I can figure out how to clip out my interruption in the middle there, where I had a bit of a audio hardware failure and could not hear Chris while apparently everyone else could. So again, let me thank you all, and hopefully this demonstrates to everyone the value that the SVC educational program brings to our community. So Chris, thank you.
My pleasure. Thank you again, Frank. Great to talk with you today.
All righty.